Okay, now let us consider the graphs of trigonometric functions. Please recall that we defined trigonometric functions for arbitrary angles kind of like this. For any angle theta, we can define sine, cosine, and tangent as y over r, x over r, and y over x. And that angle theta is arbitrary. The terminal point can be either first, second, third, or fourth quadrant, and theta value can be negative infinity, positive infinity. But we have periodic behavior, and from 0 to 2 pi, or from 0 to 360 degrees in the MS measure, we have all this entire quadrant 1, 2, 3, and 4, and anything else will be just repetition. We have to have the periodic behavior. Consequently, the graph of the trigonometric functions must share the periodic behavior, and indeed this is the graph of the sine function. Let's look at it a little bit more closely through this animation. Now in the left hand side you see a circular motion. This circle, by the way, is a unit circle for simplicity. I didn't want to get an arbitrary radius and then get extra division. I just wanted to have a unit circle. Consequently, the sine function is just vertical y. And if you look at the right hand side, the vertical, the y value is the function value. Now as we compare left hand side and right hand side, please note that the vertical distance, either positive or negative, precisely match one and the other, left hand side and right hand side. There's another thing that matches. This time, instead of looking those thick red line segments, look at these blue curved segments and line segments developing in left hand side and right hand side respectively. In the left hand side, the blue part is the arc length, the counterclockwise arc length starting from 1, 0, because that's the way the angle was defined. Well, you are dealing with a unit circle, so you don't have to divide by r, the radius, so the angle is exactly the same as the counterclockwise direction of the arc length. Division by 1 doesn't change anything. And if you look at the right hand side, it's the angle, so it's the same as the counterclockwise, the arc length. So the blue curve that's wrapping around the circle and the blue line segments that is traveling from 0 to 2 pi in the right hand side graph must match precisely. And that is the nature of the sine function. How about the sine? Sine I mean by positive or negative. And when this red bar is in the first quadrant and the second quadrant, y value is positive, and consequently the graph is positive above the x-axis. And if those go to third and fourth quadrant, or the lower half plane, then y value is negative. Consequently, we have negative portion in the graph in the right hand side. Graph goes below the x-axis. They match precisely. What if we consider the standard domain negative pi to positive pi instead of 0 to 2 pi? In that case, we are going to get this graph. The same graph, excuse me, it's not the same graph, same motion, except that it starts from negative 1, 0. So the angle develops from negative pi to positive pi, not from 0 to 2 pi. And the graph is a little bit different because we are starting from the lower half plane, and then y is starting from 0, getting smaller, 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 up until it hits negative pi over 2, or negative 90 degrees, and then comes back up and then reaches maximum at the 90 degrees, and then coming back. So we have the sine graph like this. But then again, there's no fundamental difference between this graph and the previous graph. Why? Because these are just part of a periodic behavior visible in something like this. This time, let us look at the graph of sine function from 0 to 4 pi and compare that with the rotation that is wrapping around the circle twice. So as we wrap around the circle once and then the second time, the circular motion is identical, exactly the same. Consequently, the graph is exactly the same as well. If you compare the solid graph and the dotted graph, they're precisely the same, and you're looking at the periodic behavior. And of course, the ultimate reason is because of the periodic behavior of the angle. As you wrap around the circle once or the second time around, the dynamics is exactly the same. We are looking at the same rotation, consequently the same graph. And of course, this kind of thing will continue for another 2 pi, another 2 pi, another 2 pi, and also from the negative direction as well. Consequently, what do we have? We have this kind of graph going up and down, up and down, up and down. And the feature, well, y-intercept is 0, runs to 0, comma 0 because sine of 0 is 0. We talked about those when we discussed those basic angles. And then the maximum is 1, that is obtained when theta equals pi over 2, 90 degrees. Minimum is -1, and that's obtained when when theta is negative pi over 2 or 3 pi over 2, negative 90 degrees or positive 270 degrees. Of course, sine graph is periodic, so same thing repeats over and over again. In short, we have this kind of property which is kind of visible from the graph of sine function, but it's confusing, I have to admit. Sine is between -1 and +1. That's the only thing that is really easy to see. This one, okay, it's an odd function going through the origin, and the maximum and the minimum kind of like this. But all the others, this one and all these are, what can I say, very confusing. Easy to consider because adding 2 pi will be the same because periodic behavior. Adding pi, that's basically starting from -1 comma 0, so we have to have negative of sine, and sine of negative theta, that's backward rotation, so we have clockwise rotation, so y value begins to decrease, so we have negative sine of theta, we have an odd function, things like those. Those are all simple to see from the graph or from the dynamics, but tedious. And of course, because so many negative signs are flying around, so it's a bit confusing. Do not try to memorize all these. Just prepare them somewhere, and if necessary, just bring them back. These explain the relationship between sine and cosine, but I didn't show you the graphs of cosine functions, so let's postpone that. Okay, how about the graph of cosine function? Here it is. Left-hand side, we are looking at the circular dynamics, and the right-hand side, we are looking at the graph. But I admit it's a little bit harder to see because you have to match the horizontal distance in this circle motion on the left-hand side, and then the function values are vertical in the right-hand side. So it's a little bit difficult to match, but the length of those green bars in the left-hand side circle and the right-hand side graphs must be the same, and the signs, pluses and minuses, also match. Also, please note another thing. If you look at the circular motion and this dynamics of this cosine is exactly the same as that of sine if you look at it from the sideway, from the left-hand side. So if you tilt your head a little bit, in other words, if you rotate your viewpoint about pi over 2, then the dynamics is exactly the same as that of sine. So the graph of cosine function must be exactly the same as the graph of sine function, except that it is shifted 90 degrees one way, or pi over 2 one way. And, well, by the way, this is the same graph if you draw from negative pi to positive pi, just for fun. Periodic behavior, here we go, going up and down, up and down, up and down, exactly like the sine function, except that we are starting from 1, 0 instead of 0, 0. In general, we have this kind of graph going up and down, just like sine function, except that we are starting from 1, 0 and then going down first. Similarly, we can deduce all these. Cosine function is bounded between -1 and +1. You can clearly see it from the graph going up and down, up and down. Also, you can see from circular motion too. X cannot exceed r no matter what, because hypotenuse is always the greatest. And then all those are special values. Periodic behavior, and then we have negative cosine if you add or subtract pi, because you're starting from -1, 0 backward. And then cosine is an even function. You can clearly see that from the graph and also from the circular motion and things like those. Now, if you compare sine and cosine, you will see that sine graph and cosine graph are exactly the same. You can also see that from the circular motion. If you tilt your head 90 degrees, then sine dynamics and cosine dynamics are exactly the same. It's not surprising, therefore, they are related to each other by adding or subtracting pi over 2. The only thing that is confusing is the sign, pluses and minuses. They're easy to see, yes, individually. It may be a little bit tedious, but if you put everything together, it's confusing because so many negative signs are flying around. So please do not try to memorize them all. You're not going to memorize them correctly. So write them down somewhere and then bring them back whenever things are necessary. Okay, we went through sine and cosine function, and let's go over to the tangent function. We have sufficient time for tangent, so let's go ahead and do that. The circular motion for tangent is kind of like this. Compared with sine and cosine, it's not as important, but, well, here it is, just for fun. And, well, you have to look at the ratio between vertical and horizontal. And please note that horizontal hits 0 when the terminal point hits the y-axis. X becomes 0 there. So denominator of tangent becomes 0. So that's when we have vertical asymptote. Please note that when the left-hand side hits, when this terminal point of the left-hand side hits the x-axis, hits the y-axis, when x becomes 0, we have the vertical asymptote at that precise moment. Now, and then, now, and then, now, kind of like that. So, tangent functions have vertical asymptotes. And, of course, okay, what's this for? Okay, this time I'm drawing, taking the standard domain from 0 to 2 pi instead of -pi to +pi. But it's the same deal. It's periodic everything, and we have vertical asymptotes when x value becomes 0. The same deal. In general, this is a graph of the tangent function. From -pi to +pi, we have the principal branch, and we have vertical asymptote, and same thing is being repeated over and over again with period of pi. By the way, tangent is sine of a cosine, and we're going to talk about why in a moment, actually in the next video. But if you forgive me of that, then, well, here's the relation. Putting tangent, sine, and cosine in the same viewing window, you will see that the vertical asymptote of the tangent function appears precisely when the green curve, the cosine function, hits 0.